For the second notebook of the Baltic Sea ice practical session, we are going to look at satellite observation data. In the first notebook, we looked at model products from the CMEMS portal, and this time we will look at the observation products that are available for the sea ice information. So first, as previously, we import the Python library to handle and plot the data. So I validate this cell, and I recall that to do it, you either click on this button here, run the selected cells and advance, or you can use the shortcut Shift plus Enter. There are two different kinds of observation products on the CMEMS portal for the sea ice information. One product here, which contains daily mean blended data on a near real-time basis. And this product has two different datasets, one which is dedicated to the sea ice concentration and the other one for the sea ice thickness. Another dataset or product is available for the sea ice thickness only, also on a near real-time basis, and it is based on the integration of the most recent images, and it is automatically generated. For more details about these two products, you can click on these links and you will directly access their web pages on the CMEMS portal, where you will find information from the user manual and the validation reports, and also you will find the links to download the data. A bit more about the sea ice concentration product. So it's on a 1 kilometer horizontal grid. It is provided with a daily mean product, and it's a regional product over the Baltic Sea. It's available from 2016 to today during the sea ice season only, so from December to May. And we have downloaded two subsets here for 2017, March 2017 and March 2018, that you will find in this folder here, Data Observations. So we're going to explore a first dataset from this product, sea ice concentration product. As we did in the first notebook, we defined the path and the name of the file, NetCDF file, and then we use the Open Dataset function from the Xarray library to explore the file. So you can see that it's a 3D product with latitude and on a latitude-longitude grid with 5 time frames. As I mentioned, we retrieved the data from the 3rd to the 7th of March. You can see here the date also. And there are different variables here, and this one is the one for the sea ice concentration. For the sea ice thickness, as I said, there are two different products available. So the first one, which is in the same product as the sea ice concentration, also on a 1 kilometer horizontal grid, with a daily mean temporal resolution, and available from 2016 to today during the sea ice season. So again, we already downloaded a subset of this product, and if we explore one of these files, you can see that again it's a 3-dimension product on a latitude-longitude grid with 5 time frames from the 3rd of March 2017 to the 7th of March. And here we have different variables, and this one is the sea ice thickness. The other product for the sea ice thickness we call it the sea ice thickness mosaics, is on a 0.5 kilometer horizontal grid, and it also it's provided on a daily basis but irregular basis. It's also a regional product, and it's available from 2016 to May 2020, also during the sea ice season. So if we explore one of the files that we downloaded, here you can see that, so we only extracted one date this time, so this is why we only have one time frame, and we have a higher resolution for the grid, because it's a 0.5 kilometer resolution, so we have more points for the latitude and the longitude than for the other dataset, as you can see here. And here we have the variable ice thickness. Okay, so let's compare these satellite observations for 2 years, so in March for 2017 and March 2018. So we are going to look at the first product, the one that has 2 datasets for the sea ice concentration and the sea ice thickness first. So you have 2 options, either you look at the sea ice concentration or the sea ice thickness. So here is to validate all the information for the sea ice concentration, and here is the cell to validate the information for the sea ice thickness. So you just have to validate one cell and then run all the cells for the plot. So we start with the sea ice concentration. We have 2 files here. We have defined the variable name that you want to extract and min and max values for the plot. Okay, so now I open the files. So we have 2 different files from the same product, so we can use the OpenMF dataset that enables to open several files at once and that concatenate the information over the time dimension in this case. So I validate the cell, so I have now one dataset here that contains the 2 files. So if I look at the information, I see that I have 10 time frames in this new dataset. So we have all the time frames for the first dataset in March 2017, and then the time frames for the second file in March 2018. And a point that is important for the following is that the latitude, as you can see, are stored in a decreasing with decreasing values in these files. Before generating the plots, we create a folder where we will save these plots specifically for this variable. You can see here we have a out folder, and we will create this folder for this specific plots in this out folder here. And you will be able to retrieve all the figures saved in these folders later on. Okay, so now we map the data at 2 different dates. So we have 5 dates in 2017 and 5 dates in 2018. And from the observations we made, we know that the maximum of the sea ice coverage occurred on the 5th of March 2018 for the winter 2017-2018. So we're going to look at the sea ice conditions on the 5th of March 2017 and on the 5th of March 2018. To do so, we select the date in the product using the cell function. So we define the first date here, the 5th of March 2017, the second date we want to plot, the 5th of March 2018, and we find in the product the date that corresponds to these 2 dates we want to plot. Okay, So now I have new variables, var date 1 and var date 2, which only depends on the latitude and the longitude, because we have only one time frame for each of these variables. And now we can plot the data. So we're going to plot one figure with one subplot per date. So it's exactly as we did in the first notebook. We have one subplot for each date, so one for 2017 and one for 2018. Okay, so you see the plots have been generated, and you clearly see that the sea ice concentration conditions are very different from 2017 to 2018 for the same date. And clearly the sea ice extent was really larger, much larger in 2018 than in 2017 for these dates. So you can redo exactly the same work with the sea ice thickness information by validate this cell here and then running all the cells above. So we can do it quickly. So we define the files, we load the files, so now it's ice thickness here. Then we select the dates for the plots. And I forgot to, validate this cell, which defines the path where to store the data. So I will validate this one just to be sure, and launch the plot. So you see that the figures are saved in the specific folder, and here you have the sea ice thickness for both dates, and again you can see that the conditions are quite different for these two different periods. Okay, so of course you can redo the same exercise by changing the dates, for example, at which you want to plot the data. Next exercise here is to reduce or to make a regional zoom on the data. So we're going to extract the data regionally to plot only the northern part of the Baltic Sea. So this is the plot window for the general map, and this is the extraction window. So you see that it's smaller, and it starts in the northern point, because we want to show the difference between the plot window and the extraction of the data. To do this extraction, we use again the cell function, and this time we extract slices of latitude and longitude between the lat-min, lat-max and non-min, non-max values that we have defined. And you note here that we extract the latitude between lat-max and lat-min because the latitudes are stored in decreasing values in the file. So I have now my ice thickness product, because I'm still working with the ice thickness. Still with the 10 time frames, but this time I have reduced the number of latitude and longitude points. Then I plot the data. So for this plot, as we have data for 2017 and data for 2018, we have 5 dates for each, and we are going to plot all the dates for 2017 on the first column and of our figure, and all the dates for 2018 on the second column, so that we can compare directly the date to date in the figure. So to do so, we define the axis we work on, and then we plot the data as we did previously. Okay, so now we have the plots, and you can see the very different situations. So this is for the sea ice thickness. You can see the 3rd of March 2017 and the 3rd of March 2018, and so on. So for each day in 2017 and in 2018, the conditions. Of course, you can do exactly the same for the sea ice concentration, again by validating the cells here. Okay, so now we are going to look at the two different sea ice thickness observation products. As I said, we have two different products for this, and to look at these products, we are going to load one file of each. So this time we cannot use the OpenMF dataset because these two different products are not on the same grid, and they do not have the same names of variables, so we have to open the data separately. So we have one file for each. We define the variables we want to open. We create a folder to store the plots. Okay. So here, as I mentioned, we opened the files with two different variables. Okay, and because you see that we have so 5 time frames here, so it's fine, and then we generate the plot. So we are going to plot the data only for the 5th of March 2018 because we only have this date in the mosaic product. So we need to select this date in the other observation product because we have 5 dates in this dataset. Okay, so I extract the date as we did before, and now we plot the data just as we did before. So 2 subplots, one for each product. And here we are, so we have our 2 products for the same date, and we can see that there are some differences, of course, and the mosaic product here is higher resolution, it's 0.5 kilometer, while the other product is 1 kilometer resolution. But we can see also that there are some artifacts here in this automatic product. So it's not perfect, and it's still observations. So we can see that there are differences between these two different products. For more comparisons between all the products, so the model and the observation products, you can go to the notebook 5 and notebook 6, where we compare these different CMEMS products for the sea ice concentration and for the sea ice thickness. And for the next tutorial, you can just click on this link.